In this hour, we will talk about superposition in power calculations. It may seem a bit bizarre to use the words superposition and power in the same statement because power is not a linear function of the inputs in a circuit. Okay. Consider, for instance, a very simple case, an LTI resistive circuit with a DC input, a voltage source, let's say at 12 volts. Okay, that voltage, suppose, produces a current of 1 amp through some 1 ohm resistor. Okay, so the power of that resistor is Ri square, which is 1 times 1 square, 1 watt. Okay, so if we now double the voltage from 12 volts to 24 volts, the current will also double, okay, and we will have now 2 amps of current flowing through our resistor, and that produces 1 times 2 square, 4 watts of power. Okay, so when you double the input, the power is not doubled, but it's quadrupled. Okay, the reason is that it's not proportional to the current passing through the resistor, but it's proportional to the square of the current. Okay. Having said that, there is still something that that's worth studying. Okay, for sinusoidal, for circuits in sinusoidal steady state from the power point of view, and that's what we're going to do in this hour. Namely, even though the power is not a linear function, okay, of the input, still for a circuit in sinusoidal steady state, under certain conditions, the average power does display a pseudo-linearity-like property, which allows us to apply superposition. Okay, and now we will try to figure out what those conditions are. Okay, now suppose that an LTI circuit, okay, in sinusoidal steady state, we have 2 sinusoidal sources. Okay. Now, applying the superposition principle, okay, to the current, which we can because the circuit is LTI, the current through some resistor with resistance R is, suppose I of t equals I1 of t plus I2 of t, where I1 of t is the component due to one of the sources and I2 of t is the component due to the other source. Okay, where I1 is due to the first source and the second current is due to the second source, is due to the second source. Okay, now let's look at the instantaneous power for this resistor in terms of these components of the current, I1 and I2. So let's write the instantaneous power absorbed by this resistor. Okay, now P of t is current times voltage, which can be written as R it square. Okay, now let's write I of t as I1 of t plus I2 of t. So we have I1 of t plus I2 of t squared. Okay, and that produces R I1 t squared plus R I2 t squared, and we have the cross terms. Okay, plus 2R I1 of t times I2 of t. And that can be written as P1 of t, which is the instantaneous power absorbed by the resistor when the first source is active only. That means when I1 is passing through it, plus P2 of t, which is the instantaneous power measured when only the second source is active. That is when only I2 is passing through the resistor. And then we have the cross term, I1 of t, I2 of t. Okay. Now, because of this cross term, P of t does not equal to P1 of t and P2 of t. Okay, because it's not a linear function due to that squaring operation, and we cannot therefore apply superposition to instantaneous power. So that's not surprising. We already knew that. Okay, hence P of t is not equal to P1 of t plus P2 of t. Okay, that is instantaneous power does not obey superposition. Now this seems to be the end of the story, but if we have a closer look at the average powers, which are important quantities for circuits in sinusoidal steady state, we can discover something quite remarkable and also useful from the computations point of view. And now that's what we're gonna do. So what we suggest at this point is let's have a look at the situation once again from the average powers point of view. Okay, so we ask the following question: how about the average power? Okay, namely we have three average powers and we want to figure out the relations between them, if there is a relation. And by three average powers I mean the following: the average power that we measure when both sources are active, okay, the average of P of t. Then the average power when only one of the first source is active, that is the average of P1 of t, and we have the average of P2 of t. So let's try to figure out a relation, if there is a relation between those three average powers. Okay, so P average is 1 over t, 0 to t, pt dt, which is the operation, averaging operation that we apply to signals that are periodic with period capital T. Now, if P of t is not periodic but sum or product or both of periodic signals, it can still be treated as a periodic signal, and from the practical point of view it satisfies almost all the properties that we expect from periodic signals to satisfy. Okay, so let's write that for pt, that is periodic with period t. Okay, now if, as we said, P of t is not periodic, then what we can do is we can take this capital T very, very large and define the average as the limit t goes to infinity of this integration. Okay, so let me put that down. Note, if pt is not periodic, okay, for instance, if pt is the sum of two periodic signals, it doesn't have to be necessarily periodic unless the ratio of the individual periods is a rational number. Okay, but even if it's an irrational number, then in the long run it behaves almost like a periodic function. And that for such functions we can define in a meaningful way the average value as follows. We can take P average as lim t goes to infinity 1 over t 0 to t pt dt. Okay, so let's apply that averaging operation to the right hand side. Okay, here. So what we have therefore is P average for our resistor equals 1 over t from 0 to t, P1 of t, P2 of t, plus the cross terms, 2R I1 of t, I2 of t. Okay. Now we have 3 terms in our integrand, so that allows us to write this integration as sum of 3 separate integrations. And for the first term, we obtain the average corresponding to the first source. Okay, we can write P1 average plus integral of P2t, and then normalized with respect to period, produces P2 average. Okay. Once again, P1 average is the average power delivered to the resistor when only the first source is active. Okay, so that's the power due to I1 of t, and P2 average is defined similarly. And we have 2R over t from 0 to t, I1 of t, I2 of t, dt, okay, the cross term. And let's call this cross term P12 average. Okay. Now, since we're dealing with a circuit in sinusoidal steady state, all the inputs, all the currents are of sinusoidal nature. So let's see the implication of that fact on that equation. Okay, so what we're doing is we're now working with actual sinusoidal signals. Now let I1 of t, that is the current component due to the first source through the resistor, equals I1 magnitude cosine omega 1 t plus some phase, which we call phi 1. And likewise I2 of t equals I2 magnitude cosine omega 2t plus phi 2. Okay, so omega 1 is the oscillation frequency of the first source, and omega 2 is the oscillation frequency of the second source. Okay, when both sources are active, the current is I1 of t plus I2 of t. Therefore, we see both of those frequencies. Okay, then we have P12 average, our cross term, equals 2R over t, and then we integrate the product of two cosines, I1m, I2m. Okay, these are positive constants, and cosine omega 1 t phi 1 cosine omega 2 t phi 2 dt. Okay. Now let's apply the trigonometric identity that we used already in our previous lectures. Namely, we write the product of two cosines as sums of two cosines. So this can be written as R I1m I2m divided by t. So this 2 is gone because when we do our separation of cosines, we have to multiply with the factor of 1/2. And then from 0 to t, cosine of the sums of the arguments and cosine of the difference of the arguments. Okay, so that produces cosine omega 1 plus omega 2 t plus phi 1 plus phi 2. Okay, so that's the sum of the arguments, and we also have the difference of the arguments. Okay, plus cosine of omega 1 minus omega 2 t plus phi 1 minus phi 2. Okay, dt. So that's our integral. So what we have is the following: P12 average equals, okay? Now if omega 1 and omega 2 are different, then here we have a pure cosine, and here we have also pure cosine. If omega 1 and omega 2 are different, then this is something non-zero, and then again we have a pure cosine. And when you take the average of pure cosines, pure sinusoidal signals, what you have is, you have 0 average. Okay, so when therefore these frequencies are different, omega 1 different from omega 2, this cross term, although it's present in the instantaneous power computations, when you take the average, it just disappears. Okay, and then what we'll be left with is P average equals P1 average plus P2 average, meaning that if the frequencies are different, we can apply superposition not to the instantaneous power but to the average powers, okay, in a circuit that's in sinusoidal steady state. So P12 average equals R I1M I2M cosine phi 1 minus phi 2. Now, in the other case, when omega 1 and omega 2 are equal, then still omega 1 plus omega 2 is something non-zero, and this is purely sinusoidal, and it will produce 0 average. However, this term here, omega 1 minus omega 2 equals 0, because omega 1 equals omega 2, and now what happens is this is just a constant signal, cosine of the difference of phases, and the average of the constant signal is itself. Hence, in that case, when omega 1 equals omega 2, the cross term produces something non-zero. Okay, in the other case, it produces 0. If omega 1 equals omega 2 and 0 otherwise. Okay, and now we are ready to write down the conclusion from this simple analysis. The conclusion is that if you have many sources, and if no two sources are of the same frequency, then average power can be computed through superposition. Otherwise, you have to be careful about the non-zero cross term. Okay, here is the conclusion of our simple analysis, which can be very useful or time-saving in power computations. The average power delivered to a one port by several sinusoidal sources, sinusoidal inputs in our circuit, is equal to the sum of the average powers delivered by each source acting alone, acting on its own. Okay. Under the important condition that no two frequencies are equal. Okay, provided that no two sources have the same frequency. Okay. Now, here is a nice follow-up question. How about these stored energies, okay, in capacitors or inductors? Okay, so let me write that down. How about the average stored energies for L and C? Okay. Well, it's not difficult to see that this analysis here can be easily extended to the stored energy or the average stored energy computations for inductors and capacitors, and you would have the same conclusion applying also to the average stored energies. Okay, but it's still nice to think about that question, and also if you have time it would be beneficial to redo the similar analysis for the average stored energy in a capacitor or in an inductor. Okay, now let's apply our finding to a numerical example. Okay, example. Suppose that we have the following circuit with two sources. One of the sources is sinusoidal, the other source is DC, okay, constant. Amps. We have 110 cosine 20t volts, 12 ohm, 10 millifarads, 2 ohms here, and 1/5 henries. Okay, now for this circuit driven by two sources, one DC, one AC, find the steady state IRT. This is the current passing through the 2 ohm resistor denoted by IR, and the average power delivered to the 2 ohm resistor. To the 2 ohm resistor. Okay. Now we can apply superposition to find IR of t because the circuit is LTI. Also, we can apply superposition to figure out the total of average power delivered to the 2 ohm resistor, because we have two sources and they are acting at different frequencies. So from a point of view, this DC source can also be considered as an AC source with frequency omega equals 0. Okay, so therefore the conclusion that we have reached here is applicable to this situation in our example. Okay, so since superposition is allowed, let's do that because it simplifies the analysis for this example at least. Okay, let's start with the easy case, namely DC steady state. Okay, for the DC circuit, what we have is the following. Okay. So here we had the AC source, which is a voltage source, and it's killed, meaning that that's replaced by the following short circuit. And we're dealing with the steady state case. The source is DC, therefore we're dealing with DC steady state, under which the capacitors behave like open circuits. Therefore here we have our capacitor represented by the open circuit, and inductors behave like short circuits. So this inductor, 1/5 Henry inductor, is now acting like just a wire, okay, a short circuit. And this is our I1, the component of the current due to the DC source, 14 amps. Okay, so this is 12 ohms, this is 2 ohms. Here we have 14 amps, and it will be divided between 12 ohms and 2 ohms, okay, which are now parallel. So clearly 12 amps will be flowing over 2 ohm, and the remaining 2 amps will be flowing over the 12 ohm resistor. Okay, so I1 equals IS times 12 over 12 plus 2, which is 12 amps. Okay, so this is what we measure when the AC source is killed. So once we know the current, we can also figure out the power, the average power. Since this is DC, the instantaneous power and the average power, they are equal. And what we have simply is R times the square of the current. P1 average equals 2 times I1 square. So 2 times 144, so that makes 288 watts. Okay, now let's move on to the AC circuit. Okay, and solve it using phasor domain circuit or phasor analysis. Now, AC circuit in phasor domain. Okay. Now we're killing this source. When that's killed, it means we replace it with an open circuit. So that's gone. So what we have is this part of circuit, and transforming it to phasor domain, namely replacing the components by their impedances, which is 1 over j omega c for the capacitor and j omega l for the inductor. As for the resistors, we directly carry the resistances to phasor domain. And once that's done, this is our simple circuit. Okay. 12 ohm, 2 ohm, and now we're interested in I2, the component due to the AC source. And in phasor domain, its phasor is denoted by capital I2. Okay, the source is the source is 110 magnitude and phase is 0 volts. The impedance for the capacitor is 1 over j omega c, omega 20, c 1 over 100, so that makes minus j 100 over 20, minus j 5 ohms. Okay, and as for the inductor, we have j omega l, omega 20, l 1 over 5, so that makes j 4. Okay, j 4 ohms. So let's compute I2, and once we have I2, we can easily compute the average power, because the average power is resistance times the square of the effective value of the current. And effective value of the current is the magnitude of that phasor divided by square root of 2. Okay, so what's IS? IS is the current that's leaving our source, okay, or the phasor of that current. Now IS equals 110 divided by the impedance seen by the source. And what's the impedance seen by the source? It's 12 ohm, okay, in series with this thing, and this thing is this impedance and that impedance connected in parallel. So IS therefore is 110 divided by 12 plus this impedance. This impedance is minus J5 connected in parallel with 2 plus J4. 2 plus J4 ohms. Okay. Which can be written as 110, 12 plus 20 minus J10 over 2 minus J. So this produces that, and that can be simplified to 5 amps. Okay, so IS equals 5 amps. Okay, now that 5 amps means the phase is 0. Therefore, the voltage of the phase of the voltage is also 0. So what the voltage source sees is an impedance with no reactance. Okay. Okay, so that's 5 amps, and once we have IS, this is the current, we can easily compute I2 using current division. So I2 equals minus J5 divided by minus J5 plus that impedance, which is 2 plus J4 times the source current IS. And that reads 5 minus J10 amps. Okay, therefore I2 equals 5 minus J10, but since we're gonna carry it to the time domain, it's better to write in terms of polar coordinates. So that produces, the magnitude is 5 square plus 10 square square root, so that produces 125 square root. Okay, and the phase is minus arctangent 10 over 5 minus arctangent 2 amps. Okay, and now it's easy to go to time domain. All we have to do is we have to remember the frequency of oscillations, which was 20 radians per second. So that produces I2 of t equals 5 square root of 5 cosine omega t minus arctangent 2 amps. Okay, so that's I2 of t. Combined with I1 of t will produce the current IR of t passing through the resistor when both sources are active. Okay. So we know the answer for IR of t. We can also write down the average power by simply superposing the individual average powers, because we have two different frequencies. Let's also quickly write down the average power for the second case. P2 average equals R times I2 effective or RMS square. That equals R was 2. RMS value is magnitude divided by square root of 2. 5 divided by square root of 2, and then we square that, and that produces 125 watts of average power. Okay, all that remains is combining this and that, okay, to find the average power when both sources are active, and combining this and this here to figure out to obtain the current when both sources are active. So let's write down the final answer. Finally, IR of t equals I1 of t plus I2 of t, which is this signal, a sinusoidal with some DC offset at 12 amps. plus 5 square root of 5 cosine 20t minus arctangent 2m's. And PR average equals P1 average plus P2 average. Okay. 288 plus 125, that produces 413 watts of power absorbed by the resistor on the average in steady state. Okay. Here's an exercise, another superposition exercise. This time find the average stored energy in the inductor. The answer is, okay, if I haven't made a mistake, it should be E average L should equal 133 over 20 joules, which again can be computed through superposition because we have two separate frequencies. Okay, now speaking of average stored energy in the inductor, let's talk about something that we haven't yet, namely the average stored energy in the coupled inductors. Average stored energy, okay, of coupled inductors that are part of an LTI circuit in sinusoidal steady state of inductors. Okay, so this is our device that's part of a circuit in sinusoidal steady state. The voltage, the current, and this is the voltage of the second coil. The self-inductances are L1 and L2, and the mutual inductance is denoted by N. Okay. Now, since we're assuming that this is in a circuit that's in sinusoidal steady state, I1 of t will have this form: I1 m magnitude cosine omega t plus some phase, and likewise I2 of t have the same form, some magnitude, okay, cosine omega t. They oscillate at the same frequency because everything oscillates at omega radians per second, plus phi 2. Okay. Now, the phasors of those currents are I1 equals I1 m e to the j phi 1, and I2 equals I2 magnitude e to the j phi 2. So that's the phasor representation of those two time domain currents. And from that time domain signals and also these phasor domain quantities, let's construct the vectors, because it will be quite useful to work by vector notation. Okay, so we define the current vector by simply stacking the two individual currents, I1 of t and I2 of t. And likewise, I represents the vector in phasor domain with entries I1 and I2. Now, we have already obtained the instantaneous stored energy in a coupled inductor, and we had a very nice compact formula, which was 1/2 times the transpose of the current vector times the inductance matrix times, once again, the current vector. So instantaneous stored energy reads E of t equals 1/2 I t transpose. Okay, so that's a row vector multiplied by the inductance matrix. Okay, let me write it down. L1 M L2. So this is our inductance matrix I of t. Okay, and in open form it reads the following. That equals 1/2 L1 I1 square plus N I1 I2 plus 1/2 L2 I2 square. Okay, so that's the instantaneous stored energy in our coupled device. Now the question is, let me squeeze it here. What's the average value of that number, okay, or that of that function E of t? What's average stored energy? Let's call it E average, which equals the average value of lowercase E of t. Now we will try to obtain or solve that integral, which will give us the average stored energy in our coupled device. Okay. Now this is our E of t, and we can write I1 and I2 in terms of their sinusoidal forms. And then once we have sinusoidal signals, we can start talking about computing the integral. Okay, so let's write E of t using these expressions. I1 of t is that cosine and I2 of t is the other cosine. So what we have is E of t equals 1/2 L1 times I1 of t squared. I1 of t is here, so that produces I1 m magnitude square, and then we have the square of the cosine square omega t at plus phi 1. Okay, plus the cross term n I1 I2, which produces n I1 magnitude I2 magnitude, and we have the product of two cosines. Cosine omega t plus phi 1 times cosine omega t plus phi 2. And finally we have the 1/2 L2 I2 square term. Okay, so let me squeeze it here, plus 1/2 L2 I2 m square, and we have the cosine square omega t plus phi 2. Okay, now what we're going to do is we're going to use the trigonometric identities that we used earlier, namely writing the square of the cosine as some constant term plus a pure cosine, and likewise the product of cosines as the sum of cosines. If you do that, we have the following. So that implies 1/4 L1 I1 m square. Okay, multiplying 1 plus cosine 2 times alpha. This is alpha, the argument, cosine 2 omega t plus 2 phi 1. Okay? So that's another way to write the first term. As for the second term, we have plus 1/2 m I1m I2m I2m then times the cosine of the sums of arguments and cosine of the difference of arguments, and that means we have cosine, okay, the difference is phi 1 minus phi 2 because omega t's will cancel, and we have the sum cosine 2 omega t plus phi 1 plus phi 2. Okay, so this is the second term written in a different way using the trigonometric identity. And finally, we're going to apply the same trick to the last term as we applied to the first term. So what we have is 1/4 L2I2m square 1 plus cosine of 2 times the argument 2 omega t plus 2 phi 2. Okay, this is E of t written in a slightly different way, but that slight difference will make life very easy when we compute that average. We know that pure sinusoidal signals produce zero average. So that means when you compute the average of this E of t, this term will disappear because it's a pure sinusoidal function. This term will disappear, it's pure sinusoid, and likewise this term disappears. And when those terms disappear, all the remaining terms are constant. Therefore, they directly come out intact out of the integration. And what we have therefore is the following: E average equals 1/4 L1 I1m square plus 1/2 m I1m I2 magnitude cosine of the difference of phases plus 1/4 L2 I2m square. That's the answer. But so in a sense we can stop here, but let's not stop here because this looks a little bit complicated. It turns out that by looking at this expression in a slightly different way, we can put it in a form that's very elegant and easy to remember. Okay, so we first write this as what? Okay, 1/4 L1. Now here we have I1 magnitude square. Okay, so that's the magnitude of this phasor or that complex number. So what's the magnitude of a complex number? It's simply you take the product of that complex number with its complex conjugate and then you take the square root. Since we already have squaring here, so magnitude square equals I1 times I1 conjugate. Okay, so let's write it in that way. Okay, I1 conjugate. Then we have 1/2 times m. Now here we have I1 magnitude, I2 magnitude times cosine of the difference. And that, it's not difficult to see that. That equals I1 times the conjugate of I2. Okay, you obtain the complex number with phase I1m, I2m, and, with magnitude, the product of the magnitudes, and the phase, the difference due to the conjugation of the second term. And then this then produces the real part of that complex number. In other words, this thing here can be written as real part of I1, I2 conjugate. Okay. And we have 1/4 L2, I2, I2 conjugate. Okay, now there is one last step that remains, which is to get rid of this real operator, and that can be done by L1, I1 conjugate plus, we make this 1/2, 1/4, and instead of this, what we write is I1, I2 conjugate plus I1 conjugate I2. Okay? Because real part of a complex number is complex number plus its conjugate divided by 2. And that dividing by 2 produces this 1/4 here. And finally, we have the last term. Okay. And then this now can be written compactly in matrix form. Okay. Let's do that. Let's take this here. And this equals 1/4. Note that all the terms have this factor of 1/4 times I1 conjugate I2 conjugate. We have a row vector with entries, the conjugates of I1 and I2 times L1 n L2 times the vector without conjugation. Okay, therefore, the average stored energy can be very nicely represented or computed in terms of the phasors of the currents and the inductance matrix. Because we can write 1/4 I star L I. Okay, remember that this is our L matrix, where by I star we mean not only conjugation but conjugate transposition. Okay, so this is conjugate transpose. Okay, so this here is what we're denoting by I star.